So in the yesterday's means in the last video, we have seen the definitions or you can say the types of relations. So in that 5 types we have seen: empty relation, universal relation, reflexive relation, symmetric relation, and transitive relation. Okay. So basis on these 3 standard, which one reflexive, symmetric, and transitive, we are going to simplify the examples. Okay. So based on this 3 definitions or 3 types, you will get a 3-mark question in the annual examination. Okay. So just roughly, as in the last video we have seen, I'll just revise the definition. What is that? If it is A belongs to R, means it is reflexive. It is reflexive. And next, AB belongs to R, that implies BA belongs to R. It is symmetric. It is symmetric definition. And third, AB belongs to R and BC belongs to R, that implies AC belongs to R. So this is the definition of transitive relation. Okay. Now, so based on this 3, we will solve the first exercise, that is exercise 1.1. Okay. Exercise 1.1. So in that exercise 1.1, what is the first question is, we have to determine whether the given relation is reflexive, symmetric, and transitive. Means what? Here we are going to check the given relation is reflexive, symmetric, or transitive or no. Okay. So in that first example I will take. Okay. In the question number 1, first example, they have given one set, that is 1, 2, 3, so on up to 14. Okay. So in the question, they have given one set A is equals to 1, 2, 3, so on up to 14, and defined by the relation R is equals to the set of all ordered pair xy such that 3x minus y is equals to 0. 3x minus y is equals to 0. Okay. So this slowly, this example I will explain. You just try to understand, because if you understand this one example, same method you are going to follow for the rest examples. Okay. So this set A is given and relation is given. Now this relation you have to check whether it is reflexive, symmetric, or transitive or no. Okay. Now see, one thing you have to keep in mind: if this given set is finite, I think you know this. This is countable number of elements are there, therefore it is called the finite set. So whenever it is a finite set, then this relation you have to form in a roster form. Now it is in the set builder form. I think you know this first year concept. So this form is called a set builder because it is given in the statement. Okay. If I write this in the form of ordered pairs, then it is called as what? Roster form. So whenever this given set is finite, then this relation we have to write in the finite set. We have to write this relation in the roster form. Okay. Then how to write? See here now. So this R is equals to the set of all ordered pair xy such that this 3x minus y is equals to 0. We can write as y is equals to 3x. Means minus y, transfer to the other side, we will get y is equals to 3x. Now R is equals to, and keep in mind that always this x and y belongs to the given set. Means what? This x and y should be present in given set, that is A. Okay. Now what we will do is, so x and y is there, so just go on putting the values of x from the set A. So first element is 1. If I put 1 here, x is 1, then what will get 3 ones are 3. If x is 1, then y will be what? 3. So x is 1, y is 3. Second, if I put x is 2, then y will be 6. So when x is 2, y will be 6. When I put x is 3, y will be 9. When I put x is 4, y will be 12. Okay. Now again next element is 4, next element is 5. If I put x is 5, then y will be 15. But I can't take this ordered pair. I can't take this ordered pair. Why? Because see here y is 15. Y is 15. But what I said, always this x and y should be present in the given set. And given set is up to what? 14. But it is what? 15. So therefore we can't take this. Okay? So you have to stop up to this. So now we have written this relation in the roster form. Once you write into the roster form, now we have to check those all the three conditions. Okay? The first one, reflexive. So what is the definition of reflexive? A belongs to R. Now keep in mind, suppose in the relation they have used it with x and y variable, then your definition becomes what? Here I used it with a, b and c variables. Okay. Suppose the relation is given in the form of x, y, z variables, then your definition becomes what? This will become xx belongs to R. This will become xy belongs to R, implies yx belongs to R. Next, transitive xy belongs to R, yz belongs to R, it implies xz belongs to R. Here there is usually three variables a, b, c, but in this problem x, y, z is there. Okay. So for reflexive the definition becomes what now? Xx belongs to R for all. This x belongs to which set? It is set A. Now for example, now see here x belongs to what? The set A. So this x you have to choose from the set A. So from the set A I will choose that x is 1. You can choose any one. From 1 to 14 you can choose any one. I will take 1. If I take x is 1, then this will become 1 1. Now you have to check whether this 1 1 ordered pair is present in R or no. See here, this is your R now. So whether this 1 1 is present in R? No. So therefore you have to conclude does not belongs to R. This is the example. So our real definition also becomes what? Does not belongs to R. Therefore R is not reflexive. R is not reflexive. Okay. Similarly, now you have to check for symmetric and transitive. Okay. So next definition is symmetric relation. You have to check it. So definition is what? xy belongs to R implies yx belongs to R for all xy belongs to the set A. xy belongs to the set A. Now what this relation says, you have to choose one ordered pair. You have to choose one ordered pair which is present in R. Which is present in R. If it is present in R, then its reverse should be also present in R. Okay. Now this is your R, right? So from this you choose any one ordered pair. Okay. I will take the first one. That is 1 3. Okay. This is for example. 1 3 belongs to R. Okay. This is present in R. Now we have to check whether this implies. Implies what? Y means reverse of this. Okay. So 1 3 reverse is what? 3 1. Okay. Now check it whether this 3 1 is it present in R? No. So 3 1 does not belongs to R. So if it is does not belongs to R, it means what? It does not implies. It does not implies. So therefore what can conclude? R is not symmetric. R is not symmetric. Okay. Now third one, that is transitive. So for transitive relation, what is the definition? xy belongs to R and yz belongs to R. It implies xz belongs to R. It implies what? Xz belongs to R. Means what? In the transitive relation, you have to choose the two ordered pairs in such a way that this y element must be same. Must be same. Then from that relation R, choose the two ordered pairs where this y place must be same. Okay. Now I think we should see here this one. 1 3. Okay. 3 9. So this three places same or no? So therefore, I'll take the example. So first one is 1 3 belongs to R and 3 9. 3 9 belongs to R. So what it implies? When it is xy belongs to R and yz belongs to R, what it implies? From the first order pair, first element, and second order pair, second element, it should be present in R. From the first order pair, first element is 1, and from second order pair, second element is 9. So it is 1 9. Check it, this 1 9 whether it is present in R. No. So therefore, this is does not belongs to R. And if this does not belongs to R, then we can say that so this does not imply. If it is does not imply, then what we have to conclude? R is not transitive. R is not transitive. So this is your first example. Okay. And once you complete with this all the three types, then you have to conclude. See here, R is not reflexive, not symmetric, not transitive. So hence, what you write the conclusion? R is neither reflexive, nor symmetric, nor transitive. This is your conclusion. Okay. So this is your first example. Okay. Next, we will see second example. Okay. Where again the set and the relation is given. Okay. Set and the relation is given. Okay. Let's see now. So second example is, now they have given your set is natural numbers. Which set is given? Natural numbers. Okay, and they have defined one relation. They have defined one relation. What is that relation is? That relation is the set of all ordered pair xy such that y is equals to x plus 5, and one more condition we have given, and x is less than 4. X is less than 4. Okay. If you just see the set, it is a set of natural number, then you will say that it is an infinite set. Then we should not form the roster form of this relation. But here they have put one condition: x should be less than 4. Okay, so it is a set of natural number which starts with 1, 2, and so on. And here x is what? Less than 4 means x is having only 3 values. It is 1, 2, and 3, which is countable. Therefore, it is a finite set only again. Okay, so just see now how we write this relation now. So R is equals to set of all ordered pair xy such that y is equals to x plus 5, and what are the values of x now? 1, 2, and 3, because x is less than 4. And it is a set of natural number, so starts with 1. Okay. Now we'll check the first, that is reflexive. So write the definition, that is x belongs to R. Okay. Now here for all, this x belongs to set of natural numbers. Okay. Whichever the set they will give, for that element will belong. Okay. Now for example, now this x we have to choose from the natural number. Natural numbers are what? From 1 to 3. So choose any one element. I take again 1. So if I take x is 1, then it becomes 1 1. Now this 1 1, whether it is we have to write the roster form, right? So I have not written here. Let me write that roster form first. Okay. Okay, fine. So R is equals to, okay. So if I put x is 1, if I put x is 1, 1 plus 5, that is 6. Next, if I put x is 2, y will become 7. If I put x is 3, y will become 8. So this is your relation into the roster form. Okay. Now we'll check reflexive. Okay. Definition is x belongs to R for all x belongs to the set of natural numbers. Okay. So as for example, as I told you, this x should be chosen from n. Okay, n is what 1, 2, 3. So I will take x is 1 here, it becomes 1, 1. Now this 1, 1, whether it is present in R? No. So therefore it is what? Does not belongs to R. If it is does not belongs to R, then definition also does not belongs to R. So therefore R is not reflexive. R is not reflexive. Okay. Now similarly, you are going to check with the symmetric. Okay. So we will take symmetric definition here. Okay. So definition is xy belongs to R implies yx belongs to R. Okay. Now what this symmetric relation says? Choose one ordered pair which is present in R. Okay. Here we have these 3 ordered pairs. You can choose any one. I will choose the first one. Okay. So example, that is 1, 6 belongs to R. 1, 6 belongs to R. This implies. Actually, what it says when it is xy belongs to R, its reverse ordered pair also present in R. Let us check now. 1, 6 belongs to R. Its reverse is what? 6, 1. Okay. Now whether this 6, 1 is present in R here? No. So therefore this is does not belongs to R. So therefore this is does not implies. So therefore what? R is not symmetric. R is not symmetric. Okay. Next, third relation is transitive. The definition is what? xy belongs to R, yz belongs to R, implies xz belongs to R, where this x, y and z will be what? Belongs to set of natural numbers. Again, take the example. Now see here, you have to choose the 2 ordered pairs which is present in R, but in such a way that this y element must be same. This y element must be same. Just see there and let us just check it whether we have this type of ordered pairs where we have the y will be common. Okay. See here, 1, 6 we don't have element with 6 and other element. 2, 7 don't have. 3, 8 don't have. Means what? We don't have the 2 ordered pairs in the form of this. Let's say xy belongs to R and yz belongs to R. Okay. So in the last video I have given the example of thief, okay, and judge, right? The same example you have to apply here. See, whenever you don't have the proof to show that it is not a transitive, in that case you have to conclude it is a transitive only. Okay, means what? Maybe you are having one ordered pair, but you don't have the second ordered pair with the same element here. Therefore, what? You don't have the proof to say that it is not a transitive. In that case, always we have to conclude what? R is transitive relation. R is what? Transitive relation. Okay. So here, what we can conclude the result now? R is, you can say, okay, just here, R is transitive but neither reflexive nor symmetric. Neither reflexive nor symmetric. Okay. So these are the 2 examples. Okay. So please pause the video to note it out.